In 1934, suspended inside a steel sphere no wider than a small room, the naturalist William Beebe descended into the Atlantic darkness off Bermuda and looked out through a thick quartz window into a world no human being had ever truly seen alive. The water beyond him was black, immense, and almost without familiar reference. Then, out of that darkness, points of light appeared. Shapes moved where many scientists had once imagined emptiness. A fish flashed and vanished. A drifting form seemed less like an animal than a signal. In that moment, the deep ocean ceased to be merely a depth on a chart or a place guessed at from damaged specimens hauled to the surface. It became a living realm, strange enough to unsettle not only the eye, but the habits of the mind. If you place yourself there for a moment, inside that narrow metal chamber, you can feel the peculiar tension that shaped early deep-sea science. Everything outside is real, yet difficult to interpret. Light behaves differently. Bodies look improbable. Distance is hard to judge. Even the simplest question becomes unstable. Are you seeing a creature as it is, or as pressure, darkness, and unfamiliar biology make it seem? Long before scientists could map this world with modern cameras and submersibles, they were forced to reason from fragments, glimpses, echoes, and specimens that often arrived at the surface already distorted by the journey. That uncertainty is what makes the history of the deep ocean so compelling. Again and again, the abyss confronted human beings not simply with unfamiliar animals, but with the possibility that their most confident assumptions were wrong. Some believed the deep sea was nearly lifeless. Others mistook vast moving communities for a false seafloor. Creatures now famous as icons of the abyss hovered for decades between rumor and evidence. Even when the animals themselves were finally observed, they often seemed to break the categories meant to contain them. This is the story of how scientists learned, slowly and often reluctantly, to see that hidden world more clearly. It is also the story of how the deep ocean kept resisting them, forcing new tools, new questions, and new ways of thinking about life itself. What kind of world produces creatures so unlike the ones we know best? And what does it mean when nature seems strangest, precisely where human certainty begins to fail? Picture a ship paused over very dark water, its deck wet with spray, its timbers answering the sea in small groans and shivers. Below, the visible world ends quickly. A few feet down, the surface loses its shine. Then the color leaves. Then even the idea of distance begins to fail. Men on deck feedline outward, hand over hand or through a winch, and somewhere far beneath them, a weight or a dredge sinks into a realm that no eye can follow. They cannot watch it descend. They cannot see what country of mud or stone it reaches. They can only wait, feeling the drag of the sea through rope and metal. And imagine a depth that, in the 19th century, still seemed less like an environment than a negation. The surface of the ocean could be crossed, charted, sailed, and fought upon. The deep lay outside ordinary experience. It was cold, black, silent, and under a pressure that many educated people took to be almost self-evidently fatal. Before it became a place of animals, it existed in the scientific imagination as a place where life would fail. That first mistake did not arise from stupidity. It grew out of a very human habit of extending the known world until it meets the unknown, and then assuming the pattern will continue. Near the shore, life could be gathered, described, sorted, and named. as naturalists sampled deeper water, the returns often seemed to grow poorer. Fewer familiar forms appeared. The bottom came up bleak, the catches smaller, stranger, more uncertain. In the 1840s, the British naturalist Edward Forbes, working from dredging observations made in the Aegean, noticed this apparent thinning of life with depth and pushed that pattern outward by extrapolation. In 1843, he proposed what became known as the Azoic hypothesis, the idea that below about 300 fathoms, the deep sea was effectively lifeless. To modern ears, it sounds like a dramatic failure of imagination. But in its own time, it possessed the severe elegance of a logical conclusion. Darkness without end, bitter cold, crushing pressure, and very little reason to suppose food could reach such depths. All of this seemed to point toward a barren floor. Forbes was wrong. But he was wrong in a way that reveals how science often begins, not with fantasy, but with reasonable overconfidence built from incomplete evidence. Forbes himself was not a marginal figure talking wildly at the edge of respectable science. He was a serious naturalist, energetic, intelligent, and widely admired. The kind of investigator whose conclusions carried social weight because they appeared to rest on direct contact with nature. That matters. The idea of an empty abyss did not spread because people preferred emptiness as a story. It spread because the conclusion seemed to fit both the data available and the Victorian faith that nature, properly observed, could be ordered into zones, laws, and limits. There was also a subtle psychological comfort in the hypothesis. A lifeless deep kept the ocean conceptually continuous with human intuition. It allowed the unknown to remain harsh but legible if shallow waters nourished, and great height on land turned barren. Then perhaps the deepest sea, like a mountain summit turned upside down, could also be imagined as a sterile extreme. The hypothesis transformed mystery into boundary. It told science where life ended, and once a boundary is drawn by a confident mind, later evidence rarely arrives into a neutral space. It arrives into a structure of expectation, where awkward facts must first fight to be seen. Yet the awkward facts were already there, floating at the edges of the story. In 1818, during Arctic sounding work, a brittle star was reportedly brought up from great depth, an early sign that the deeper sea was not as empty as some later theorists would claim. From about 1850 onward, stronger evidence began to accumulate from Norwegian waters, where Michael Sars and his son Gorg Osian Sars found animal life at bathyal depths, precisely where the reigning idea predicted a biological fading toward nothing. Later, Charles Wyville, Thomson and colleagues would sample still deeper waters during the cruises of HMS Lightning and HMS Porcupine. In retrospect, the record can look almost ironic. The case against the Azoic Deep did not arrive as one perfect revelation. It accumulated in fragments, in organisms attached to sounding lines, in dredges that contradicted expectation, in specimens that did not belong inside the theory but existed all the same. The deep sea was already beginning to answer back. The trouble was that answers from the abyss tended to reach the surface weakened, delayed, and easy to dismiss. An idea can remain powerful long after it has begun to fail, especially when the world it governs is difficult to witness directly. It helps to linger for a moment with the physical reality of that difficulty. Even when a dredge returned with signs of life, the evidence came up through a punishing journey. Pressure changed. Delicate bodies tore. Colors vanished. Soft tissues collapsed into formlessness. Mud coated everything. Imagine standing on deck as the winch complains, and the dripping mouth of the apparatus rises from the sea. The crew leans in. A smell of brine and rot opens into the air. Among stones, ooze, shell fragments, and broken matter, someone notices a star-shaped body, or a worm, or a creature unlike anything familiar from shallower coasts. Was it truly from the bottom? Had it drifted in? Was it damaged beyond trustworthy interpretation? The 19th century did not yet possess submersibles, remote cameras, or the confidence that comes from seeing an organism alive in its own setting. It possessed labor, patience, rope, steel, and human judgment under uncertain conditions. This is why the empty abyss remained plausible longer than it should have. The deep did not merely hide life. It interfered with the process by which life becomes evidence. And when evidence becomes unreliable, absence begins to look more orderly than strangeness. What finally began to change the intellectual climate was not a single triumphant specimen, but a widening sense that the old picture no longer fit. By the late 1860s and early 1870s, deeper dredging in the North Atlantic had pressed the case further than Forbes's original framework could comfortably contain. Charles Wyville Thomson was especially important here, partly because he brought technical skill and scientific authority to the question, and partly because he understood that the problem of the deep sea was bigger than any isolated curiosity. It touched the geography of the ocean, the circulation of water, the distribution of temperature, and the range of life under conditions once assumed impossible. The cruises of Lightning and Porcupine did more than recover organisms. They made the abyss newly thinkable as a domain of research rather than an abstract terminal zone where inquiry could only end. That shift matters for the mood of the century. Once the deep becomes a place instead of a limit, it begins to attract a different kind of attention. Curiosity no longer asks merely whether something can live there. It begins to ask what kind of world must exist for such life to be possible. Then came the voyage that has entered scientific memory almost as a threshold event. On the 21st of December, 1872, HMS Challenger left Portsmouth on a global expedition that would continue until 1876, taking measurements and collecting samples across the world's oceans. Its scientists and sailors recorded observations from hundreds of stations, gathered deep-sea material on a scale never previously attempted, and returned with evidence so abundant that the old vision of a dead abyss could no longer retain its authority. The expedition would later be described as the real beginning of modern oceanography. Its findings were published across 50 volumes, totaling nearly 500 pages. More importantly for this story, Challenger demonstrated that deep-sea life was not an anecdotal exception, but a recurring fact. Animals appeared on abyssal plains that had once been imagined as sterile. Thousands of new species were described from the voyage, and the ocean floor itself began to seem less like a blank beneath navigation, and more like a vast inhabited geography whose strangeness had been masked by human inaccessibility. There is something worth noticing in the emotional structure of this discovery. When people speak of scientific progress, they often imagine the gradual conquest of ignorance by method and discipline. That picture is partly true. But the early history of deep-sea biology suggests something subtler. The first great advance came not from understanding the deep in detail, but from losing confidence in a tidy falsehood. A boundary had to collapse before a world could appear. In that sense, the deep ocean entered science twice. It entered first as a place where life was thought to end, and then again as a place where that ending failed to occur. The second entrance is the more profound one, because it forced naturalists to confront a possibility that science always finds difficult and fruitful. The possibility that nature has not merely withheld information, but arranged itself in ways that make our intuitions poor guides. The darkness below was not empty. It was simply under no obligation to resemble the shallow sea, the land, or the forms of life human beings knew best. Seen from this angle, the strange creatures of the deep do not begin as monsters. They begin as a philosophical problem. What sort of assumptions had to be surrendered before such creatures could even be imagined as real? The answer is more revealing than it first appears. Scientists had to loosen the habit of treating human comfort as a measure of possibility. They had to stop assuming that darkness meant emptiness, that pressure meant death, that cold implied sterility, and that what was difficult to sample could safely be declared absent. The transformation was intellectual, but it was also psychological. It required a kind of restraint, a willingness to let the ocean say no to elegant conclusions. In time, this change would open the way to stranger questions about glowing bodies, improbable anatomies, giant forms, parasitic fusions, and ecosystems that flourish without sunlight. But none of that could happen until the first great error had been removed. Before the deep sea became crowded with wonders, it had to cease being imagined as a void. And even then, the victory was not complete. To admit that the abyss held life was only the beginning. The creatures that rose from those depths did not arrive as clear answers. They came altered by pressure loss, broken by machinery, muddied by the floor, stripped of movement, and separated from the conditions that gave their bodies meaning. The old emptiness had been abandoned, but certainty did not replace it. A new problem now stood waiting on deck, under lantern light, inside jars and trays and notebooks. If the deep was inhabited, what exactly had the ocean sent back to us? And how much of it had changed on the way? That next question, quieter and in some ways more difficult, is where the descent truly begins. And so the next uncertainty gathered not in theory, but in the wet shine of specimens laid out under human light. On deck, after hours of waiting, the apparatus finally rose dripping from the water column, carrying with it a confusion of mud, shell fragments, broken stalks, worms, crustaceans, scraps of tissue, and forms so altered by the ascent that even their original posture had vanished. The men sorting through the haul were not standing before an orderly revelation. They were handling remains that had traveled upward through cold, darkness, and immense pressure into air, warmth, and touch. Some animals arrived torn by the machinery itself. Others had softened, collapsed, or lost the very textures that made sense of them where they lived. In jars, trays, and notebooks, the question of life at great depth gave way to a quieter and more intricate challenge. Once something had been brought back, how could anyone know what it had really been? This difficulty ran deeper than inconvenience. It shaped the very logic of natural history. In a meadow, a forest, or along a rocky shore, a naturalist could observe an organism in place, compare individuals, watch its movement, and perhaps return to see it again. Creatures from far below did not permit that kind of intimacy. Their environment was missing from the record almost as completely as their motion. Mud adhered where context should have been, delicate appendages detached, Colors that might have mattered in life turned pale in death, or changed again in preservative. The body on the table was real enough, but it was real in the wrong condition. Much of 19th century work on animals from great depth therefore took place in a strange intellectual atmosphere, one in which a specimen could be both the best evidence available and an unreliable witness to its own original form. Pressure was part of the story, although not always in the simple manner popular imagination later preferred. It is tempting to picture every animal from far below exploding as it rises. But the reality depended on structure and physiology. Some fishes from depth, especially those with gas-filled spaces, could indeed arrive with bodies badly altered by decompression, their tissues displaced or swollen in grotesque ways. Other creatures had no such gas spaces, yet were still vulnerable because their bodies were built for a different physical world. Gelatinous animals could lose their coherence almost at once. Soft invertebrates were easily shredded in the dredge or damaged by the long pull through the water. Crustaceans and shelled forms sometimes survived the trip in better shape, which meant that early science was biased not only by where it sampled, but by what could physically endure being sampled. The record tilted toward the robust, the armored, the compressible into taxonomy. That bias mattered. It meant that the first image of life in the lower reaches was shaped by survivorship before it was shaped by understanding. Hard-bodied animals reached museums more readily than fragile drifting forms. A creature with a shell, carapace, or firmer skeleton had a better chance of becoming a scientific fact than one built like living glass or jelly. Entire ways of being alive could disappear between the bottom and the surface. If later generations would come to associate darkness below with monstrous teeth, long jaws, or armored oddities, part of the reason lies here, in a practical asymmetry of evidence. The animals easiest to collect were not necessarily the ones most representative of those habitats. They were the ones most likely to remain legible after violence. Hauling, storage, and transport. Preservation introduced another layer of transformation. Alcohol and formalin were indispensable to 19th century and early 20th century zoology. Yet they did not freeze an organism in perfect truth. Tissues shrank, transparent bodies clouded, pigments faded or shifted, delicate membranes crumpled against glass. A body that had moved in 3 dimensions through black water was pressed into the stillness of a container and asked to submit to description. Naturalists were well aware of these problems, but awareness did not abolish them. It only made the act of description more fraught. Measurements could still be taken, teeth counted, plates compared, appendages sketched. Yet those measurements and sketches rested on a body already translated from one world into another. What science preserved, in many cases, was not the living animal itself, but a damaged version stabilized long enough to be named. Naming was never a trivial act. To assign a species, a genus, a family, or an anatomical interpretation was to declare that a fragment belonged within the known order of life, or else that the order itself needed adjustment. In this respect, the creatures hauled up from great depth produced not only visual unease but taxonomic pressure. They arrived with combinations of traits that could look implausible, exaggerated, or incomplete. Was an unusual specimen truly a new form, or merely a juvenile stage of something already known? Had its body been deformed by the haul? Was that strange extension a natural structure, or the artifact of injury? Even today, zoology can be slowed by limited material. In the 19th century, when whole lineages were less fully mapped and communication between institutions took time, these uncertainties were magnified. The scientist at the table did not just see a specimen. He saw a branching set of possibilities, and any one of them might harden into error if chosen too quickly. A good example of how the lower world reached science through partial survivals can be found in the history of giant isopods. When Alphonse Milne Edwards described one of these great crustaceans in 1879 from material gathered in the Gulf of Mexico, the animal was startling enough on its own terms. An outsized relative of familiar woodlice, scaled up to a size that seemed almost theatrical. Yet what made it taxonomically secure was not simply its strangeness, but its durability. Here was a body with hard external structure, jointed limbs, and enough physical integrity to survive collection and examination. Science could meet it more easily than it could meet a drifting gelatinous form that dissolved into anonymity on contact. That difference shaped cultural memory as well. The giant isopod became one of the emblematic creatures of great depth, in part because it could arrive as itself, or close enough to itself to persuade it was alien. Yes, but convincingly alien, a thing the museum could hold. Not every animal cooperated so neatly. The frilled shark, first formally described in the 19th century from specimens taken off Japan, seemed at once archaic and difficult to place within public imagination. Later popular culture would exaggerate that quality, turning it into a kind of living fossil caricature. But even in more sober scientific terms, the animal unsettled expectation. Its body did not fit the sleek, familiar image of a shark shaped by coastal and pelagic species better known to European and American audiences. The head, the many gill slits, the elongated form, the teeth, each feature made sense anatomically. But together they carried a strong impression of something out of sequence, something that had bypassed the usual visual education of naturalists and the public alike. Yet even here, the specimen remained only a beginning. A preserved shark can yield measurements, dentition, and morphology, but not the rhythm of its movement in darkness, not the full look of its skin in life, and certainly not the feel of the environment that shaped it. Again and again, zoologists found themselves working at this uneasy boundary between certainty and reconstruction. The great reports of expeditions such as Challenger were monumental achievements, but their authority rested on countless acts of judgment carried out amid imperfection. Specimens had to be sorted, compared with earlier collections, illustrated by hand, shipped, re-examined, and fitted into systems that were themselves evolving. Some were fragmentary. Some existed in only one or two known examples. Some represented sexes or life stages so different from one another that they could easily invite misclassification. When later readers opened the grand printed volumes of 19th century marine zoology, with their engraved plates and measured prose, they encounter the end product of a process that now looks serene. It was not serene at all. Behind each clean plate lay uncertainty, argument, and the low-level anxiety of deciding whether one was looking at a true novelty or at damage disguised as nature. The physical labor behind this work is easy to forget because the language of classification can sound so still. But the route from the lower reaches to the scientific page passed through bodies and hands. Sailors hauled lines in weather that could turn sampling into exhaustion. Assistants rinsed mud from metal baskets and tangled nets. Curators unpacked leaking containers months later. Artists translated dim, softened remains into clean visual form. In that sense, the knowledge of these animals was built in layers of mediation, mechanical, bodily, artistic, conceptual. One reason errors persisted is that every layer introduced the possibility of interpretation. A missing appendage could be accidental or diagnostic. A color note might reflect life, preservation, or decay. A contour drawn by an illustrator might subtly regularize a body that in reality had collapsed. The scientific image often looked more coherent than the evidence from which it had been built. There was also the matter of desire. Quiet, disciplined desire, but desire nonetheless. Naturalists wanted order. They wanted forms that could be compared, descriptions that could stabilize, names that would endure. That wish was not vanity. It was part of the scientific temperament of the age. And without it, taxonomy could not proceed at all. Yet the lower reaches often punished the longing for neatness. The hall might contain juvenile forms impossible to match with adults, parasitic relationships not immediately recognizable, or bizarre morphologies that tempted premature generalization. A damaged body could easily invite a more reasonable interpretation than an intact but unfamiliar one. In other words, the mind sometimes repaired reality before understanding it. The danger was not merely that the world below was hard to sample. It was that the human intellect, faced with broken evidence, naturally tried to smooth it into familiarity. Some of the most important absences in this story are therefore invisible in museum drawers. Countless fragile organisms must have been lost before they could be studied at all. Transparent predators, drifting colonial forms, gelatinous animals with bodies designed more for buoyancy and fluidity than for endurance. Such creatures likely vanished from early collections in large numbers or reached institutions in shapes too compromised to reveal their significance. This is one reason the historical image of those zones developed unevenly. The lower fauna first entered science through a filter that favored hardness, segmentation, teeth, spines, and shell. The softer architectures of life were present, but they were far harder to convert into records. Long before cameras ever descended, the lower world had already been edited by the mechanics of recovery. That editing affected theory as well as description. If the creatures easiest to collect were scavengers, crustaceans, benthic forms, or animals with more durable anatomy, then ideas about the nature of life at depth would naturally lean toward what those specimens suggested. Ecological imagination lagged behind taxonomy. Scientists could name what arrived without fully grasping how those animals related to one another, how many had been missed, or how different the living assemblage might look in motion. A tray of sorted bodies implied a stillness that was never truly there. It encouraged thought in terms of objects rather than processes, isolated species rather than layered communities. In the absence of direct observation, the living environment was repeatedly reconstructed from what could survive disassembly. That was an extraordinary achievement and a profound limitation at the same time. By the late 19th century, it had become increasingly clear that the challenge was not merely to gather more material, but to gather better kinds of evidence. Natural history could go a long way with patient comparison and preserved bodies. Yet there remained questions that jars could not answer. How did these animals hold themselves in the water? Which colors mattered in the dark, and which disappeared? What forms were ordinary in life but looked absurd in death? Which apparent oddities were structural, and which were scars of ascent? The more zoologists learned, the more sharply they felt the boundary of what specimen-based knowledge could provide. The world below had ceased to be empty. but it had not yet become visible in any ordinary sense. Science possessed the remains of lives whose setting was still almost entirely imagined. And that produced a peculiar intellectual mood, halfway between possession and blindness. Museums filled, descriptions multiplied, families and genera expanded, yet something essential continued to evade the page. The lower fauna had been proven real, but it had not yet fully entered experience. Scholars could classify an animal and still have only the faintest idea of how it appeared when alive in its own medium, moving through its native darkness instead of lying stilled beneath laboratory light. The difference between those two states was larger than many readers of the great reports could easily appreciate. One was anatomy, the other was existence. Sooner or later, that difference would have to be confronted directly. Because if the living truth of those creatures could not be recovered from broken bodies alone, then someone would have to do something far more difficult than dredging the unseen. Someone would have to descend toward it and look. Someone, in time, did, on the morning of June 11th, 1930, off Nonsuch Island in Bermuda. A steel sphere about 4.5 feet across hung from a cable above the water, swinging slightly before its descent. It was called the bathysphere. Inside, two thin men had folded themselves into a space so cramped that comfort had long since stopped mattering. One was Otis Barton, the engineer who had helped bring the vessel into existence. The other was William Beebe, already well known as a naturalist and writer, now preparing to exchange inference for direct witness. On deck, Gloria Hollister took her place by the telephone line and expedition log, ready to catch whatever could be spoken from below before darkness swallowed it again. The bathysphere was simple in one sense and audacious in another. It had no power of its own. It did not swim, steer, or roam freely. It was lowered and raised by a ship at the surface, tethered by steel and dependent on oxygen tanks, soda lime, and a telephone wire that linked its occupants to the world above. Yet simplicity was part of its daring. Earlier investigators had studied animals from great depth by dredging, trawling, and sorting what survived the trip upward. Beebe wanted something different. He wanted to see living forms where they belonged, in the water column itself. Before ascent, damage and preservation rewrote their bodies. That ambition marked a real change in marine science. It was no longer enough to ask what could be retrieved. The more radical question was what might be learned by looking directly into an environment still almost absent from human experience. That wish had a psychological force to it as well. Beebe had spent years working with animals, writing about them, and cultivating an unusual balance of scientific seriousness and literary intensity. He was not a narrow specialist, content to leave wonder outside the laboratory door. He seems, from the record, to have believed that close attention and excitement were not enemies, that to witness a creature alive in its own setting was in some sense a higher form of truth than merely owning its remains. Hollister understood that feeling too. In a journal entry written shortly before one early descent, she wrote of her desire to go down in the sphere and see with my eyes and not my imagination. It is a striking line because it captures the deeper motive of the whole enterprise. The bathysphere was not simply a machine for breaking depth records. It was a machine built to reduce the distance between evidence and experience. The physical experience of going down in that vessel was far from serene. As the sphere descended, the interior cooled. Condensation formed overhead and dripped down into the cramped cabin. The occupants sat on curved steel, managing air circulation with improvised means, checking seals, listening for the health of the apparatus as much as looking outward through its quartz windows. The view itself was limited, framed by small portholes that forced the eye to search darkness in fragments. There were technical problems too, sometimes frightening ones. The expedition faced electrical faults, severed communication lines, leaks, heavy weather, and the constant possibility that a failure in the wrong place would leave the men inside not merely isolated, but trapped. Even before the scientific questions began, the act of descent had already stripped away the illusion that this was a neat extension of ordinary observation. And yet, once the bathysphere had gone down far enough, the surrounding water began to offer something no dredge ever could. Beebe could watch animals pass rather than infer their existence from broken pieces. He could note the way bodies held themselves, the way flashes of light announced an organism before its shape became legible, the way colors narrowed as depth increased. During the dives, he dictated observations nearly continuously to the surface, both to record what he saw and to demonstrate that the line of communication still held. Hollister, listening and transcribing, was therefore far more than a passive observer of someone else's triumph. She was the memory of the descent while it was happening, the disciplined mind at the other end of the wire, converting fleeting sight into usable record. In this sense, the first human witnesses to life at depth were never only the people inside the sphere. They also included the ones who received, organized, and preserved those moments above. That is one reason Gloria Hollister deserves to stand near the center of this story rather than at its edge. She most often handled the surface end of the telephone line, taking down Beebe's descriptions in real time, and she later made her own descents in the bathysphere, setting ever deeper records for a woman diver, including a dive to 208 feet in 1934. She was also a scientist in her own right, working on fish osteology and refining methods for clearing and staining specimens to reveal bone structures. The historical image of early deep-sea exploration can easily collapse into a story about one charismatic man peering through a window. But the actual labor was broader, more collaborative, and more intellectually distributed than that. Hollister's role makes this visible. The descent produced meaning only because someone above was able to hold on to the torrent of spoken impressions and turn them into a scientific trace. Over the course of the bathysphere program, Beebe and Barton made dozens of dives off Bermuda between 1930 and 1934, with many of them pushing beyond previous human depth limits. Their record-setting descent on August 15th, 1934 reached 3,028 feet, essentially half a mile down, and remained a landmark in human descent for years. But the numerical records, however dramatic they looked in newspapers, were not the most important legacy of those dives. Their lasting significance lay in the shift from recovered specimens to living observation. Up to that point, marine biologists had depended overwhelmingly on trawls, nets, and dredges for knowledge of depth fauna. The bathysphere did not replace those methods, but it introduced another standard by which claims could be judged. A living fish seen moving through darkness was not the same kind of evidence as a body hauled upward and preserved in fluid. Beebe himself seems to have understood the distinction very clearly. He had experience with trawled material and could therefore recognize how much was lost when a body was divorced from its environment. From inside the sphere, he could identify certain animals by their luminous patterns alone, something impossible to reconstruct from a dead specimen. He was also attentive to gradients of color and light, noting how the visible spectrum changed with depth. In the lower water column, perception itself became part of the scientific problem. One did not simply see an organism. One saw it under altered optical conditions, at the edge of visibility, sometimes first as a point of light, sometimes as a passing silhouette. This gave the bathysphere observations a special quality. They were not only about anatomy, they were about presence, behavior, spacing, approach, withdrawal, and atmosphere. Life there was suddenly dynamic rather than merely collectible. That change in perspective also altered the emotional tone of the science. Reading the earlier expedition reports, one often senses patience, rigor, and caution, but little immediacy. The bathysphere brought back immediacy in abundance. Here were descriptions delivered live from a realm that had previously existed for most readers as an abstraction. NBC even broadcast one of the descents by relaying the line from Hollister's station, allowing listeners on land to hear a mediated version of a scientific encounter taking place below the surface. That public dimension helped make Beebe unusually famous. It also contributed to an uneasiness that would follow him. Celebrity can widen the audience for science, but it can also make some colleagues suspicious that performance has displaced rigor. Beebe's career would end up touching both sides of that tension. He was, in some ways, unusually vulnerable to that suspicion. Beebe wrote vividly. He attracted attention. He worked with artists such as Elsa Bostelmann, whose paintings, based on notes and recollections from the dives, became some of the expedition's most memorable visual documents. Those paintings were scientifically motivated, yet they also carried the atmosphere of a world hovering between biology and dream. For supporters, that was part of their power. For skeptics, it could look uncomfortably close to dramatization. The question beneath the debate was an old one in science. When an environment is so difficult to access that direct recording remains limited, how much trust should be granted to expert observation shaped by memory, transcription, and illustration? The bathysphere did not eliminate the problem of mediation. It simply moved mediation into a new form. This became especially delicate because Beebe went further than some of his contemporaries were prepared to accept. During the bathysphere years, he described a number of fishes from visual observation alone. Later scholarship notes that 4 of those species, based solely on what he saw through the porthole, were never formally accepted and became the center of a lingering controversy in ichthyology. Carl Hubbs, in a 1935 review of Half Mile Down, criticized this aspect of the work sharply. Yet the historical picture is more complicated than a simple tale of gullibility or fraud. Later assessments argue that Beebe's scientific reputation likely suffered in part because of those visually described species, and also because his fame as a public figure may have made fellow scientists more wary. At the same time, much of his broader portrayal of the lower water column has since been judged impressively accurate, especially when compared with later submersible observations and imaging. That mixture of insight and dispute is one of the reasons Beebe remains such a compelling figure. He occupied a threshold position. He was trying to create a science of direct witness in a place where instruments were still primitive. Recording technology was limited, and observation itself could easily outrun what could be verified. If he had stayed within the narrower safety of specimens alone, he might have avoided some criticism. But then he would also have failed to open the path he did. There is a quiet irony here. The very ambition that made the bathysphere historically important, the desire to observe living animals in their own surroundings, also produced data that were harder to stabilize according to conventional standards of proof. Science advanced, but not without friction. The first eyewitnesses to that realm enlarged knowledge while also exposing how uneasy knowledge becomes when it outruns the methods available to secure it. For Hollister, the meaning of the work seems to have been equally practical and visionary. Her transcriptions preserve a rhythm that feels almost like a pulse of attention. Depths called out, glimpses noted, colors thinning, forms appearing and vanishing before full certainty could settle around them. Her own descents confirmed that the sphere was not only a place for records and publicity, but a genuine observational platform, however constrained. And the wider team around BB, including technical staff and artists, reminds us that the first living portrait of these depths was assembled collectively. It passed from porthole to voice, from voice to notebook, from notebook to image, from image to publication, and then into public imagination. Even the most direct witness was still part of a chain. That chain could distort. Certainly, it could also, when handled with care, carry something astonishingly new into the realm of human thought. What changed, then, was not simply that people went lower than before. The alteration was subtler and more lasting. A region once known largely through damaged bodies and inference had now been encountered as an inhabited vertical space, filled with motion, light, and passing forms whose behavior mattered as much as their anatomy. Direct observation did not solve every difficulty. It introduced fresh ones, but it restored something specimen-based science could not provide on its own. The fact that these animals were not just structures to be classified after death. They were actors in an environment with its own visual logic. The significance of that shift is hard to overstate. It changed the scientific imagination from one oriented around retrieval to one oriented around encounter. And once encounter had entered the story, another possibility opened with it. If a human observer, peering through a tiny quartz window, could suddenly perceive scattered flashes and bodies suspended in darkness, then perhaps the darkness itself was far less empty than anyone had guessed. Perhaps what looked sparse to the eye from one moving sphere was, at another scale, a crowded and restless domain. The next great surprise would come when technology stopped trying merely to descend through that realm, and instead began, in its own peculiar way, to listen to it, only to discover that the waters below were capable of giving back an answer so large that, at first, it resembled a false bottom moving in the night. By the time instruments began to listen for what human eyes could not follow, the problem changed shape once again. A watcher in a bathysphere had seen flashes, silhouettes, fragments of motion. Sonar operators, years later, encountered something stranger. Their machines were not offering glimpses of individual lives. They were returning a boundary. During the Second World War, ships using echo-sounding and active sonar sometimes detected a strong reflecting layer suspended well below the surface, often a few hundred feet down. It behaved like a bottom, or at least like something broad and solid enough to send sound back with unusual force. Yet it was not fixed where a bottom ought to be. In some areas, it shifted. In others, it seemed to vanish. And as crews compared readings taken at different times of day, an unsettling pattern began to emerge. The layer was not staying put. For men using acoustic instruments in wartime, this was first and foremost a practical irritation. Sound was supposed to clarify distance, reveal underwater hazards, help distinguish one kind of target from another. a phantom boundary complicated all of that. It did not belong neatly to navigation, and it did not belong neatly to combat either. Something in the water column was producing a return strong enough to imitate structure, then quietly changing depth under cover of darkness. In the tense logic of war, ambiguity has a way of becoming its own problem. Off the California coast, researchers working on long-range sonar noticed that the strange layer seemed to rise toward the surface at night and sink again after dawn. That simple behavioral rhythm made the mystery more difficult, not less. A rocky ledge does not climb upward at sunset. Sediment does not descend with morning light. The feature was acting less like terrain than like a population, though that conclusion was still awkward to name. An instrument built to measure the world was suddenly reporting something that behaved as if the world itself were alive in a new way. That is one of the most interesting psychological turns in this history. When a device draws a line, the mind wants to believe in a line. Machines seem to reduce doubt. A trace on a paper recorder or a pulse returned from below carries a kind of stern authority. Earlier generations of naturalists had struggled with torn specimens, uncertain illustrations, and fragile bodies changed by the journey upward. Now technology appeared to offer a more objective encounter, and yet here too, certainty slipped. The machine was registering something real, but the reality arrived wearing the wrong disguise. At first, several explanations remained possible. Perhaps the signal came from a layer in the water where temperature changed sharply enough to affect sound. Perhaps bubbles, debris, or suspended matter were distorting the reading. Perhaps the equipment itself was at fault. That range of uncertainty is worth lingering over, because it shows how marine science often advances. A signal appears. It seems concrete. Then, rather than solving the world, it multiplies the number of ways the world might be misunderstood. Some of the earliest reports treated the feature almost like a charting nuisance. On nautical maps and survey records, doubtful underwater forms sometimes appeared and then dissolved under later scrutiny. There is something quietly haunting about that archival stage of knowledge. Before the scattering layer was understood biologically, it entered human records as a suspected topography that could not quite be trusted. The lower world had already misled science through absence, through damaged specimens, through the limits of direct observation. Now it was doing so acoustically, creating the impression of a place where there was only a concentration of moving life. The shift toward a biological explanation came gradually, and it required a certain flexibility of mind. One had to be willing to accept that the returning signal might not represent a passive surface at all. Marine biologists such as Martin W. Johnson at Scripps began to think along those lines. Johnson was deeply familiar with planktonic life and with the subtle, often invisible structures that organize marine communities. If the layer rose in darkness and sank again in daylight, the pattern hinted at behavior. It suggested animals responding to light rather than rock or mud, occupying depth. The idea was not entirely without precedent. Long before sonar, naturalists had noticed that tiny aquatic organisms could appear and disappear according to time of day. Vertical movement in response to changing light had already been observed in lakes and upper waters. But sonar gave that older intuition an astonishing new scale. If a living layer could reflect sound strongly enough to mimic a bottom, then the number of organisms involved had to be immense. This was not a curiosity of a few drifting bodies. It was a vast, coordinated movement. That realization did not arrive in a single flash. It had to be tested. In 1945, Johnson and colleagues carried out around-the-clock net sampling in waters where the mysterious acoustic layer had been recorded. The key was timing. If the depth of the false bottom changed over the course of the day, then biological sampling had to change with it. Nets were sent through the same levels where the acoustic return had appeared. What came back aligned with the machine's behavior. Dense concentrations of animals occupied those depths, and as darkness came on, those concentrations shifted upward. The phantom layer was not a mistake in the instrument. It was the instrument's way of reporting a crowd. From there, the picture widened. The feature that sonar had mistaken for a seafloor became known as the deep scattering layer, a region in the water column packed densely enough with animals that sound waves bounced back from it as though they had struck something solid. Many kinds of organisms contributed to that signal. Small fishes with gas-filled swim bladders were especially important because gas reflects sound efficiently. But they were not alone. Crustaceans, squid, gelatinous animals, and other midwater life all helped create this acoustic veil. The false floor turned out to be less like a single sheet and more like a living band whose composition could vary from place to place. Once the biological explanation settled in, the old wartime nuisance transformed into one of the most significant ecological discoveries in marine science. Each evening, great numbers of organisms rise toward upper waters, where phytoplankton-fueled food is more abundant. Under cover of darkness, smaller animals feed, larger ones come up to feed on them. Then, with returning daylight, the movement reverses. The band sinks again into dimmer water. And with it sink trillions of bodies avoiding the gaze of visual predators above. Seen one way, this is simply animal behavior repeated on a daily cycle. Seen another way, it is almost difficult to think about without enlarging one's sense of scale. The vertical migration associated with the deep scattering layer is often described as the largest migration on Earth. That phrase can sound inflated until the mind slows down long enough to absorb what it implies. Across vast stretches of the global ocean, night after night, an enormous proportion of marine life rises and falls through the water column in response to the changing geometry of light. This is not a seasonal spectacle visible from land. It happens continuously, quietly, beyond ordinary perception. And here, the emotional texture of the documentary changes again. Earlier, the story moved through absence, fragments, rare glimpses, and contested witness. The scattering layer introduced a different astonishment. The world below was not only populated, in places it was crowded past any intuitive human scale. A man in a steel sphere might see one fish drift through darkness and feel he had encountered a marvel. Sonar, in its colder way, revealed multitudes. It heard the density of life before science fully understood what that density contained. That discovery also altered ecological thought. A vertically migrating band of animals is more than a biological curiosity. It feeds predators. It redistributes energy. It helps transport carbon downward as animals consume food nearer the surface and later respire, excrete, or die at greater depths. In other words, this nightly migration is woven into planetary processes. The acoustic mystery that once interfered with naval measurements turned out to be part of the machinery by which the marine world breathes, feeds, and moves matter through the planet. There is a special kind of irony in that progression. Sonar had been designed for military and navigational purposes, not to reveal an immense hidden migration. Yet the instrument succeeded precisely because living bodies possess physical properties that sound can register. Swim bladders, tissues, shells, clusters of organisms. All of them became accidental participants in a conversation with technology that had not originally been built for them. Science has often advanced like this, through tools that discover more than they were asked to find. Even so, the deep scattering layer did not solve the mystery of midwater life. In some respects, it made that mystery larger. A region once imagined as sparsely inhabited now appeared thick with organized motion. But the individual animals within that movement were still only partly known. Which species dominated in different places? How did moonlight alter the timing of ascent? How many forms remained acoustically present yet biologically underdescribed? The line on the sonar screen had yielded one secret and opened many others. That is the pattern beginning to reveal itself by now. First, there was the confident emptiness of the azoic hypothesis. Then came specimens altered by the journey upward. Then the narrow, astonishing witness of a descent through a quartz window. Now sound had uncovered a realm dense enough to mimic terrain. Each step brought science closer, and each step also showed that closeness itself could mislead. The lower ocean did not simply hide facts. It translated them into forms that humans were liable to read incorrectly. And once you begin to think that way, another possibility becomes easier to accept. In a world capable of concealing a moving population so vast that machines mistook it for geography, individual creatures could remain elusive for a very long time. Some would become famous in rumor long before they became clear in science. Some would drift through culture as monsters, half seen and half invented, while evidence arrived only in fragments. The darkness below, now known to be crowded, was still perfectly capable of keeping a few of its most iconic inhabitants at the edge of certainty. So it is not difficult to see how, in a realm dense enough to fool sonar and distant enough to resist ordinary witness, certain animals could linger for decades, even centuries. In that unstable territory between evidence and story, sometimes they entered human knowledge, not as living bodies observed in place, but as torn arms, strange scars, fragments in a whale's stomach, or a carcass hauled ashore in poor condition. By the time such creatures reached public view, they were already wrapped in projection. A mind confronted with something large, pale, many-limbed, and unfamiliar does not begin from calm taxonomy. It begins from older habits, fear, exaggeration, analogy, the urge to compare the unknown with monsters already waiting in culture. Few animals illustrate that more clearly than the giant squid, which spent an extraordinarily long time being culturally oversized before it became scientifically visible. Long before zoologists settled on the name Architeuthis, enormous squid-like bodies were being folded into myth, Smithsonian Ocean. Notes that people who found large dead specimens in earlier centuries often did not know what they were looking at, and the animal's sheer oddness encouraged fantastic interpretations. In 16th century Denmark, strange carcasses were described as sea monks, part human in appearance, because observers tried to force the unknown into familiar symbolic forms. By the mid-19th century, the Danish zoologist Japetus Steenstrup argued that these supposed marvels were in fact very large squid, and in doing so he performed a subtle but important act of scientific demystification. He did not abolish wonder. He changed its object. The astonishing thing was no longer that the ocean had produced a monster from folklore. It was that ordinary cephalopod anatomy, scaled up and glimpsed badly, had proved enough to generate centuries of imaginative confusion. The public life of the giant squid intensified in the 19th century because the evidence became harder to ignore. In late 1873, the Reverend Moses Harvey in Newfoundland bought a dead giant squid from a fisherman, displayed it in his home, and helped circulate what Smithsonian Ocean describes as the first photograph ever taken of a giant squid, the animal draped over a bathtub for study and display. It is one of those scenes that feels almost too strange to be historical. But that strangeness is exactly the point. Science did not first meet the giant squid in a pristine laboratory setting. It met it in parlors, ports, newspapers, sketches, rumors, and salvaged carcasses that were both invaluable and awkwardly theatrical. By then, fiction was already helping to amplify the animal's image. Jules Verne had woven a monstrous squid into 20,000 Leagues Under the Sea, giving popular culture a version of the creature that would remain much easier to picture than the actual biology. What followed was not a clean replacement of myth by fact. It was a long coexistence. Enough evidence accumulated by the late 19th century to convince zoologists that giant squid were real animals rather than sailors' fantasies. Yet the manner of that evidence kept the creature suspended in a peculiar half-light. Most of what scientists knew, and to a large extent still know, came from bodies found dead at the surface or washed ashore, not from repeated observation of healthy adults in their natural environment. Smithsonian Ocean puts it plainly: giant squid live far below the surface, are rarely seen, and most of what we know has come from carcasses found by fishermen. That is a perfect recipe for cultural distortion. The animal is too real to dismiss, too hidden to normalize, and too large to stop feeling symbolic. That tension shaped the career of Clyde Roper more than almost anyone else's. Roper, a Smithsonian zoologist who specialized in cephalopods and became the most famous giant squid expert of his generation, devoted years to pursuing an animal he knew mostly through bodies, fragments, and the marks it left on its predators. In one Smithsonian reflection, he recalls dissecting a sperm whale that had washed ashore in Florida, hoping to find a giant squid in its stomach. Instead, he found large circular scars around the whale's head and mouth, evidence of the struggle between predator and prey. That detail says something essential about the scientific life of the giant squid. For decades, one of the clearest proofs of its ordinary existence came not from seeing it directly, but from reading its violence on another animal's skin. Roper's search later extended to expeditions in places like Kaikoura Canyon in New Zealand, where he and others hoped to film a living specimen in waters frequented by sperm whales. Again and again, the animal remained just beyond reach. There is a particular psychology to chasing a creature like that. A scientist can spend an entire career gathering enough evidence to know an animal is real, ecologically important, and probably not even especially rare on a planetary scale, while still failing to meet it alive. Smithsonian Magazine wrote in 2005 that Roper was still the world's foremost authority on Architeuthis, even though he had never seen a living adult. That fact gives the story much of its power. In many fields, expertise grows through repeated direct contact. Here, authority had to be built from indirect traces, damaged specimens, and relentless comparative work. Roper's own writing later described the giant squid as a mysterious, wonderful and real monster, a phrase that captures the balance he spent his career maintaining. He did not surrender the word monster entirely, but he kept insisting on the final word in the phrase: real. When the first known photographs of a living giant squid were taken in 2004, And when a giant squid was filmed in its natural habitat in 2012, those moments mattered for more than their visual novelty. They marked the slow collapse of a peculiar historical spell. Smithsonian Ocean notes that the species was first recorded live in 2006 after bait was suspended beneath a research vessel, and that the first filming in its natural habitat followed in 2012. For the public, this felt like confirmation of a creature long associated with rumor and cinematic exaggeration. For scientists, it provided something quieter and more important: continuity between the dead bodies in museum collections and the living animal in its own environment. The giant squid had not changed. Human access had, what dissolved, at least a little, was the gap that had allowed myth to swell in the absence of direct encounter. Yet the giant squid is only the most famous case. Other animals from great depth have lived under different versions of the same distortion. The frilled shark, for example, is easy to cast in the role of living fossil or sea serpent survivor. Smithsonian Ocean describes its snake-like body, frilled gills, and rows of three-pronged teeth. And even on a simple species page, the animal seems to arrive already burdened with analogy. Is it an eel? A relic? A prehistoric holdover? Part of the answer is visual. Human beings are strongly drawn to body plans that appear to violate the categories we think we know. A shark that does not resemble the sleek, torpedo-shaped image of a shark familiar from modern media is quickly recruited into older narratives about primitive survivors and deep-time monsters. The scientific reality is more restrained. The frilled shark is a rare and little-seen species adapted to very deep water, and its feeding behavior has not even been directly observed. It remains mysterious, but not in the way popular imagination prefers. That difference matters because the word monster tends to erase scale, ecology, and context. It converts difficult animals into symbols of the unknown, which makes them culturally powerful but scientifically flat. The frilled shark is a good example of how an unusual body can attract layers of projection with very little evidence attached. The animal's long, dark form and archaic-looking dentition encourage a narrative of ancient menace, while the actual scientific literature remains comparatively thin because sightings are rare and the species lives where direct behavioral observation is hard. The result is an asymmetry similar to what surrounded the giant squid, though on a smaller stage. Public familiarity arrives before biological familiarity. The image stabilizes before understanding does. A creature becomes famous for being itself only approximately. Modern technology has not ended this pattern. It has only changed the kinds of animals that inherit it. Consider the big fin squid, an animal that looks less like the classic sea monster of old illustration and more like a sketch from speculative fiction. No-A Ocean Exploration notes that it has only been about 20 years since the big fin squid family was officially described by scientists, and that only roughly a dozen sightings had been confirmed worldwide by 2021. Even that phrase, officially described, hints at how recent and fragile the scientific record still is. Here is an animal now recognized as globally distributed in the deep ocean, capable of living deeper than any other known squid. And yet for most people, it entered awareness not through biology textbooks, but through eerie video clips passed around for their sheer uncanniness. The body seems almost designed to resist immediate interpretation. Oversized fins, extremely long arms and tentacles with elbow-like bends, proportions so bizarre that the first reaction is often to question what one is seeing. Even the way big fin squid appear on camera preserves something of the old uncertainty. NOAA notes that in one of its sightings, before the camera zoomed in, the animal was initially thought to be a siphonophore or jellyfish. That detail is small, but revealing. In the age of remotely operated vehicles and high-definition imagery, the lower ocean still produces moments that begin as misrecognition. Vision has improved enormously since the era of carcasses and bathtub photographs. Yet the first encounter can remain unstable, with bigfin squid. The instability extends into taxonomy and life history as well. Adults are largely known from video observations, while the family itself was described comparatively recently from younger specimens. Scientists continue to infer behavior from anatomy, suspecting that the long arm tips may trap prey as they hang or drag below the body. But direct observation remains limited. It is an animal that has entered science and still, in some ways, not fully arrived. There is a continuity here across centuries that is easy to miss if one focuses only on technology. Early modern Europeans found giant squid remains and imagined sea monks. 19th century readers saw giant carcasses and thought of Verne. 20th century and early 21st century viewers watched rare footage of bigfin squid and described them as alien, ghostly, or impossible. The metaphors change with culture, but the underlying habit remains steady. When an animal appears rarely, looks unlike familiar near-surface forms, and resists repeated study, the human mind reaches quickly for narrative scaffolding. Sometimes that scaffolding comes from folklore, sometimes from natural theology, sometimes from horror cinema or science fiction. Scientific knowledge does not float above those impulses. It develops beside them, sometimes against them, sometimes helped by the very fascination they generate. That is why these creatures occupy such an important place in the history of marine science. They reveal that evidence alone does not control the shape of understanding. Evidence must circulate through newspapers, museums, lecture halls, documentaries, paintings, expedition reports, and popular memory. The giant squid became a scientific object, in part because people could not stop talking about it. Roper's career, with its mixture of technical expertise, public outreach, and almost mythic persistence, sits right inside that overlap. Even his archival record at the Smithsonian reflects a life spent not only researching cephalopods, but exhibiting them, explaining them, corresponding about them, and keeping them before the public eye. The scientist in such a story is not merely correcting myth from the outside. He is negotiating with it, redirecting it, trying to let fascination survive while falsehood shrinks. And perhaps that is the more interesting lesson. These animals did not remain shadowy simply because they lived far down in darkness. They remained shadowy because they reached us through partial encounters that invited narrative inflation. A scar on a whale, a body in a fisherman's net, a shark with a body too serpentine for comfort, a squid whose limbs seem to go on longer than the camera expects. Each of these is enough to start a story long before it is enough to finish one. Science advances by patiently refusing the finished story. It returns to the carcass, the photograph, the specimen jar, the video frame, and asks for less poetry and more precision. But it cannot entirely avoid the emotional charge that brought attention to the animal in the first place. Some creatures become famous because they are known. Others become famous because they are still, in important ways, not known at all. And once that thought settles in, another shift becomes possible. If certain animals remain trapped for so long between rumor and reality, Part of the reason was that human beings were still trying to interpret them through shapes. Teeth, tentacles, and body plans alone. The next breakthrough would come from a different direction, from the recognition that down there, appearance is only part of the story, and that some of the most important signals are written not in outline or anatomy, but in flashes, glows, lures, and brief coded lights moving through the dark. And once certain animals had spent so long trapped between rumor and anatomy, another realization slowly came into view. Shape alone was never going to be enough. Far below the reach of sunlight, life often announced itself first as a flash, a pulse, a wink, a moving point that existed for an instant and then was gone. To human beings, light usually means illumination. It helps us see things. In the midwater and below, however, light is frequently part of the thing itself. It is not merely what reveals an animal. It is one of the ways the animal acts, hides, hunts, warns, and communicates. That shift in perspective changed everything, because it meant that many of the most important clues were not written in body plans at all, but in fleeting signals that older methods were poorly equipped to read. Marine bioluminescence had been noticed for centuries in one form or another. Sailors had long described glowing wakes, shining breakers, and water that seemed to catch fire under an oar. But the lower ocean posed a different challenge. There, luminescence was not an occasional spectacle near the surface. It was woven into ordinary survival. Modern analyses, drawing on hundreds of thousands of observations, suggest that about 3/4 of animals in the water column are capable of bioluminescence, and that the proportion remains remarkably high across depth. MBAR-IS summarizes the finding in simple terms. Roughly 3/4 of life in the water column can make its own light. Once that figure is allowed to sink in, the old image of darkness as absence begins to give way to something more intricate. The dark below is not empty of light. It is full of privately generated signals, most of them brief, many of them purposeful, all of them part of an ecology the human eye was never designed to parse on its own. That ecology is difficult to understand if we cling too tightly to surface intuitions. In our world, light usually exposes. In theirs, it can erase. Smithsonian Ocean notes that many animals use photophores on their undersides for counter-illumination, matching the dim light from above so that a predator looking upward sees less of a silhouette. A squid or fish that would otherwise appear as a dark cutout against the faint brightness overhead can dissolve into near invisibility by producing its own downward glow. There are other uses as well. The deep-sea anglerfish draws prey close with a glowing lure, one lit by symbiotic bacteria housed in the eske. Cookie-cutter sharks exploit luminous undersides to entice larger animals near enough to bite. In each case, the light is doing something quite specific. It is camouflage, bait, misdirection, invitation. The same physical phenomenon becomes many different meanings depending on who is seeing it and why. Once you begin to think of light that way, the lower ocean starts to resemble a place of coded exchanges rather than a simple dark void punctuated by pretty effects. Some flashes are defensive, some courtship-related, some predatory, some almost certainly still misunderstood. Smithsonian Ocean describes ostracods and psyllid fireworms using luminous signals in reproduction, while other creatures deploy light in moments of alarm or confusion. The functions can overlap. A display bright enough to startle a predator may also attract a second predator. A body glowing in one wavelength may be conspicuous to one species and effectively invisible to another. This is why the word language fits, as long as it is handled carefully. The animals are not speaking in any human sense. Still, they are producing signals that exist only because another creature, or several creatures, are likely to interpret them. Light here belongs to interaction. It is not decoration. It is behavior made visible. For much of the 20th century, scientists trying to study this realm ran into a frustrating paradox. The animals glowed, but the tools humans use to observe them often overwhelmed the very phenomena under study. Bright white lights from submersibles and remotely operated vehicles could startle or drive away light-sensitive organisms. Noisy hydraulic systems added another disturbance. In other words, the observer arrived carrying sensory violence into a place where subtlety mattered. NOAA's description of the Medusa system says this plainly. Bright white lights and the noise generated by large deep-diving ROVs are likely to scare off animals adapted to life in darkness. That observation sounds almost obvious once stated, but it required a major conceptual adjustment. Earlier generations had focused on reaching greater depth, stronger lights, bigger machinery, clearer footage. Edith Witter helped push the field toward a different question. What if seeing more required doing less? Witter is such an important figure in this story because her contribution was not simply to collect new images. She changed the ethics of observation. A specialist in bioluminescence and later a MacArthur Fellow, she spent years paying close attention to how animals respond to artificial light and to the peculiar visual physics of dark water. WHOI recounts a turning point for her in the 1980s, when she became fascinated by how creatures living near the edge of darkness had evolved both to see faint light and to make it. Over time, she grew increasingly frustrated that conventional submersible methods were thwarting the very behaviors she wanted to record. If you illuminate the scene with a flood lamp and announce your presence with engine noise, what follows may reveal far more about the animal's reaction to you than about its ordinary life. Witter's genius was to treat that interference not as an unavoidable inconvenience, but as a scientific problem that could be designed around. Part of the solution came from understanding what many animals below can and cannot see. Red wavelengths are quickly filtered out as depth increases, and NOAA notes that red light effectively never reaches the deep ocean. That is why so many red animals in deep water appear black and therefore inconspicuous. It also opened a methodological possibility. If most inhabitants of those depths are tuned primarily to blue light, then long wavelength red illumination can, within limits, function almost like a covert flashlight. Witter modeled one of her systems after the stoplight loosejaw, a dragonfish known for the unusual ability to emit and perceive far red light, a rare capacity in that environment. WHOI describes it as one of the few creatures down there capable of both producing and sensing red light. By borrowing that trick, Witter and her collaborators could watch with a color most surrounding animals would scarcely notice. That idea took practical form in the Eye in the Sea and later in the Medusa, camera systems designed to observe unobtrusively rather than dominate the scene. NOAA explains that the Medusa uses red lights invisible to most deep-sea inhabitants and avoids noise-generating thrusters, allowing it to function as a stealth observer below the twilight zone. It could be left in place, patient and comparatively quiet, rather than arriving like a bright mechanical interruption. The contrast with earlier modes of exploration is striking. Instead of forcing visibility onto the environment, these systems waited for the environment to disclose itself. Scientific progress here did not come from more aggressive penetration. It came from restraint, from accepting that the animals already possessed a sensory world of their own, and that understanding them required entering that world with greater tact. Witter's second insight was even more elegant. If the lower ocean is full of creatures responding to light as signal, then perhaps a camera should not merely hide itself. It should learn to speak, or at least imitate speech convincingly enough to attract interest. For that, she turned to a jellyfish called a tola. When disturbed, a tola can produce a dramatic circular display of blue light, the sort of intense pattern that Witter and others have associated with the burglar alarm hypothesis. The idea is that a small animal under attack may emit a conspicuous luminous display that draws in a larger predator, one capable of attacking the first attacker and thereby giving the original victim a chance to escape. In the 2007 oceanography article, Sly Eye, Witter describes these displays as the marine equivalent of an alarm call. Many animals in the water column, she argued, are effectively crying out with light. That was more than a poetic image. It became a piece of engineering guidance. The result was the E-jelly, an optical lure built to imitate the luminous disturbance display of a tola. NOAA's Medusa materials explain that the electronic jellyfish was designed specifically to mimic the bioluminescent display of this common jellyfish and attract animals into the camera's field of view. This is a remarkable turn in the history of science. For generations, people had tried to study unfamiliar marine life by pulling it upward, chasing it, trapping it, or blasting it with enough light to force it into view. Witter's approach asked a subtler question. What signal would a predator in that environment already be primed to notice? Instead of overpowering the local rules of perception, she borrowed them. The camera did not simply watch. It participated in an existing visual system, carefully and selectively, in order to reveal who answered. This was not a theoretical triumph alone. NOAA states that Witter's innovations helped produce footage of rare sharks, squid, jellyfish, and crustaceans, and ultimately led to the first recordings of the giant squid in its natural habitat. WHOI adds that with the far red lighting system and the E-jelly, Witter was the first to record video evidence of a giant squid while filming off Japan in 2012. That achievement belongs partly to the previous section's long story of rumor and elusive evidence. Here, though, its significance is methodological. A supposedly monstrous animal came into view more clearly when science stopped behaving like a loud intruder and started behaving more like a patient listener using the right phrase in the right sensory register. The same principle has continued to matter for observing less famous organisms as well. Many creatures reveal ordinary behavior only when human presence is softened enough for them to ignore it. The beauty of this shift lies in how many layers of understanding it brought together at once. Bioluminescence was no longer merely a biological curiosity to catalog. It became a key to vision, camouflage, signaling, predation, and research design. Consider the anglerfish again. Its lure is not simply an eerie ornament. Smithsonian Ocean explains that the deep-sea anglerfish's glowing esca is created by symbiotic bacteria and used to draw prey toward the mouth. Or consider the many fishes and squids that use counter-illumination to erase their own silhouettes. Or the stoplight loosejaw, carrying its private red beam through a world where most eyes cannot detect that wavelength. Every one of these examples enlarges the field of thought. The lower ocean is not only inhabited by creatures that shine, It is organized by visual strategies, by selective visibility, by the management of attention under extreme darkness. The science becomes richer when it stops asking only what produces light and begins asking for whom is this light intended. There is also a broader history of ideas lesson here. Human beings often assume that better knowledge comes from making the world brighter. More illumination, more exposure, more control. Bioluminescence in the lower ocean complicates that assumption. Too much of the wrong light can make understanding worse. It can flatten a carefully tuned visual environment into something foreign and misleading. Witter's work stands as a beautiful example of science learning humility from its subject. She did not merely discover a set of glowing animals. She accepted that those animals were already solving perceptual problems in ways human technology had barely begun to understand. By adapting cameras to their sensory conditions, she showed that progress can mean becoming quieter, dimmer, more patient, more willing to let another world remain itself while you study it. And once that lesson is absorbed, another threshold opens. A world full of coded flashes, covert lures, concealed silhouettes, and signals directed at unseen receivers is already strange enough. But there remained an even deeper surprise waiting below. If animals could build whole visual languages in darkness, then perhaps they were also living within ecosystems far more elaborate than older science had guessed. Communities sustained in ways that did not depend directly on sunlight at all. The next great turn in the story would begin when researchers descended toward places where the ordinary surface logic of life seemed, at first glance, not to apply, far below the reach of daylight, where the water is cold enough to feel conceptually clean and final. The seafloor near a mid-ocean ridge can look, at first, almost lunar. Basalt, fractures, sediment in thin patches. The long stillness of a place that seems cut off from the ordinary theater of life above. Then the lamps catch something wrong with that picture. The water itself appears to shimmer, as if the world has gone slightly out of focus. A plume rises where no fire should be. White shells lie in clusters, and standing among them are long, pale bodies topped with red plumes, too numerous to be written off as accident, too vigorous to fit comfortably inside older assumptions about what darkness at such depths ought to allow. The first people who came close to this scene were not searching for animals in any simple sense. By the mid-1970s, geophysicists had become interested in a heat flow puzzle along mid-ocean ridges. Newly formed crust at spreading centers ought to have been releasing more heat than some measurements seemed to show. One possible answer was that seawater was circulating down through fractured rock, heating up, then returning through vents elsewhere. It was an elegant geological idea. It kept the mystery inside the earth, where it belonged, and did not yet ask biology to do anything surprising. That is what makes the discovery so memorable. Part of it had already been imagined correctly. Hydrothermal circulation was not itself the shock. The surprise arrived when the cameras and submersibles found life assembled around it in thick, unmistakable communities. In 1977, researchers working near the Galapagos Rift used the towed camera system Angus and then the submersible Alvin to investigate a region where hydrothermal activity was suspected. The first clues were visual and oddly subtle. There was shimmering water, the optical distortion caused by warm vent fluid meeting the surrounding cold. There were mounds and fresh-looking geological features. Then there were the animals. Clams in great beds, towering tube worms, organisms arranged around venting fluids in a density that did not look like the sparse scavenging many people might have expected from life, dependent only on the slow fall of organic debris from surface waters. You can almost feel the scientific mood changing inside that descent. A geological anomaly is one kind of problem. A thriving biological community around it is another. Heat leaking from crust can be absorbed into established models. Dense animal assemblages force a different pace of thought. They press harder. They ask for an explanation immediately. The 1977 expedition did not answer everything on the spot, because it could not. In fact, one of the most revealing details in the history of the discovery is that the first expedition had not even brought biologists as principal participants in anticipation of such a find. That absence tells you how narrow the original expectation had been. The seafloor near the ridge was supposed to clarify a geophysical process. Instead, it opened into a question about the energetic basis of animal life in darkness. 2 years later, in 1979, scientists returned with that question fully alive. By then, the scene was no longer simply astonishing. It had become intellectually urgent. If these communities were not being fed in the familiar way, then what sustained them? The visual drama of the vent field was already enough to secure its place in the history of exploration. But history of science moments are not made by spectacle alone. They become transformative when a place begins to rearrange the logic of explanation. The answer emerged through microbes. That sentence sounds small compared with the imagery of giant tube worms and vent plumes. Yet it carries the real force of the discovery. Researchers found abundant bacteria associated with vent fluids and vent animals. And those microbes were using chemical energy from compounds such as hydrogen sulfide to fix carbon into organic matter. No sunlight was required. The foundation of the food web was chemical rather than photosynthetic. The vent field was not simply hosting a few extraordinary animals eking out an existence on drift from above. It was supporting a locally powered ecosystem. At that point, the intellectual ground shifts under your feet a little. Not because photosynthesis ceases to matter in the wider biosphere. Of course it does. But because the old mental picture of darkness changes shape. Darkness had often implied dependence, thinness, borrowing. These communities did borrow nothing in the simple way one might have expected. They drew on an energy source rising through the crust, through chemistry, through the disequilibrium between hot reduced fluids and cold oxidized seawater. The seafloor, in a sense, had become part of the food web. The tube worms helped make this reality visible because they were so large, so strange, and so difficult to forget once seen. The giant tube worm can reach lengths that make it seem less like a worm than like an upright structure. White tube below, red plume above. Yet the most interesting part of the animal is not obvious from the outside. Adult tube worms have no digestive tract in the ordinary sense. Inside them is a specialized organ called the trophosome. Packed with symbiotic bacteria, the worms absorb hydrogen sulfide, oxygen, and carbon dioxide from the surrounding water and deliver them to their bacterial partners. The bacteria, in turn, perform chemosynthesis and provide organic carbon. A body that looks singular turns out to be metabolically collaborative. That kind of partnership altered how many scientists thought about the boundary between organism and environment. A tube worm could not be understood simply by describing its anatomy in isolation. Its existence was tied to fluid chemistry, microbial metabolism, and the physical instability of vent habitats. One could no longer keep biology neatly separate from geology, or the animal neatly separate from its internal symbionts. To understand one, you had to hold all of them in mind at once. And the tube worms were only part of the story. Around vents were clams and mussels with their own microbial relationships. Crabs and fish exploiting the local abundance. Mats of bacteria coating surfaces. Later discovered vent fields with different dominant species. Different chemistries, different visual signatures. The original find near the Galapagos Rift opened a door, but beyond it was not a single ecosystem repeated endlessly. It was a whole class of ecosystems, varied and regionally distinct, each shaped by the chemistry of vent fluids, the age of the site, the tectonic context, and the evolutionary histories of the species present. That was one reason the discovery deepened rather than simplified with time. The first encounter produced a clean shock. There is abundant life here, in darkness, supported by chemistry. But as more sites were found and more dives were made, the picture grew more textured. Some vent fields were dominated by giant tube worms. Others were marked by dense mussel beds or shrimp swarms. Some were relatively stable for years. Others changed rapidly with volcanic and tectonic events. A vent community was not a fixed tableau arranged for human astonishment. It was a dynamic system subject to colonization, disturbance, succession, and disappearance. Cindy Lee Van Dover belongs to this second phase of the story, where discovery had to mature into ecology. She joined the first biological expedition to hydrothermal vents on the East Pacific Rise in 1982, and later became the first woman qualified to pilot Alvin. That biography matters, but not only as a milestone, it places her right at the hinge between first wonder and long-term understanding. By the time Van Dover entered the field, vent biology was no longer merely about proving that such communities existed. It was about asking how they worked, how they differed from ridge to ridge, how larvae crossed the vast gaps between isolated sites, and how life persisted in habitats that might shut down geologically without warning. One of the most beautiful examples of that deeper phase came from the Mid-Atlantic Ridge. There, instead of the famous giant tube worms that had come to symbolize vent life in the Pacific, scientists encountered fields thick with shrimp. Van Dover later helped show that one of these shrimp species had unusual, light-sensitive organs on its back. That detail does more than add another curious adaptation to the catalog. It reminds you that even within these chemically powered ecosystems, animals were still solving old sensory problems in new ways. Darkness remained darkness. Predation remained predation. Evolution kept working on perception, feeding, reproduction, and habitat use, even while the energetic base of the community was so different from the sunlit systems people knew best. There is something almost chastening in the way the vent story unfolded. At each stage, the human mind wanted to settle too quickly. First, the lower ocean was imagined as barren. Then it became populated, but still fundamentally dependent on food raining from above. Then a spectacular vent field appeared, and one might have been tempted to treat it as an anomaly, a freakish exception. But the more carefully scientists looked, the more it became clear that vent ecosystems were neither impossible nor trivial. They were a robust expression of life's capacity to exploit available energy wherever physical conditions allowed. That widening effect reached beyond marine science very quickly. Once researchers accepted that rich communities could be based on chemosynthesis, the older category of habitable environment began to loosen. The connection to astrobiology came almost naturally. If microbial life and its associated animal communities could flourish in darkness around hydrothermal systems on Earth, then icy moons with subsurface oceans, chemically active rocky worlds, or ancient extraterrestrial environments no longer seemed quite so easy to dismiss. The vent field did not prove life elsewhere. It did something more subtle and perhaps more important. It made certain forms of extraterrestrial speculation intellectually respectable, even on Earth, though the implications were large enough. These ecosystems force scientists to think more carefully about how life and planet are braided together. Heat flow from the crust, seawater circulation through rock, mineral chemistry, bacterial metabolism, symbiosis, larval dispersal, ecological succession. Each one alone belongs to a different disciplinary habit. At vents, they had to be thought together. A ridge was no longer just a tectonic feature. A worm was no longer just a worm. A plume of chemical-rich water was no longer merely a geophysical emission. Everything there crossed explanatory boundaries. And as often happens, the better the science became, the more complicated the ethical picture grew. Hydrothermal vent fields are not only biologically remarkable, they are also associated with seafloor massive sulfide deposits rich in minerals that industry has learned to value. So the same places that reoriented biology, microbiology, and planetary imagination now sit inside discussions of extraction and regulation. For scientists such as Van Dover, the story has therefore expanded once more, from discovery to ecological understanding to conservation. Once you know what these systems are and how rare and unstable some of them may be, it becomes impossible to view them as abstract curiosities alone. That, perhaps, is the deepest emotional shift in the vent story. At first, the scene looks impossible. Then it becomes legible. Then, after enough years, it becomes vulnerable. And somewhere inside that arc lies the real historical importance of the discovery. Hydrothermal vents did not merely add another strange habitat to the list of Earth's marvels. They weakened a habit of thought. They made it harder to assume that life's essential conditions are obvious to creatures like us, living in the thin illuminated layer near the surface, in darkness, around chemical energy rising from the crust. Whole communities had been carrying on for ages without fitting comfortably inside the expectations of surface minds. By this point in the documentary, that pattern should feel familiar. Human beings kept approaching the lower ocean with categories shaped elsewhere. And again, those categories proved too narrow. Yet the next step takes the challenge inward, even more sharply. Because after you accept that ecosystems can flourish where sunlight never arrives, another question begins to press. What happens when the individual creatures themselves begin to strain the very words we use for body, identity, anatomy, and even what counts as a single animal? By now, after so many revisions of what the lower ocean could contain, the pressure begins to fall somewhere stranger than geology or ecology. It falls on language itself. There are creatures down there that do not simply look unusual, or behave in unexpected ways, or survive under conditions once thought impossible. They interfere with the categories by which human beings normally organize the living world. You can feel that interference almost immediately in the names people give them. Vampire squid, giant siphonophore, parasitic anglerfish, giant isopod. Each name reaches for something familiar, then falters as soon as the animal begins to resolve into detail. The words hold for a moment, then loosen in the hand. Take the vampire squid, perhaps the most elegantly misleading name in the whole documentary. Its scientific name, Vampiroteudis infernalis translates to something like the vampire squid from hell, and for a long time, the animal's appearance encouraged exactly that kind of theatrical reading. Dark body, cloak-like webbing, large eyes that can seem red under certain conditions, a silhouette that looks made for folklore rather than quiet biology. Yet Smithsonian Ocean is wonderfully blunt about the error built into the name. Despite its demonic look, the vampire squid is not a fierce predator haunting the lower water column. It lives slowly in dark, low oxygen water, and feeds by gathering drifting particles of marine snow with two long filaments. Even its family relationships bend expectation. Contrary to its common name, it is more closely related to octopuses than to typical squids. That combination of traits is what makes it so revealing. It is easy to imagine science correcting a myth by replacing it with something cleaner and simpler. But the vampire squid does something subtler. It remains visually uncanny even after the old assumptions fall away. The animal still looks dramatic, still glows, still moves through a region of low oxygen that many other active predators avoid. It can curl its arms back over its body in a defensive posture that makes it appear almost to turn inside out. And it can produce luminous defensive displays when disturbed. Yet the real surprise is gentler than the name suggests. It survives by patience, by collecting sparse organic debris, by living at low metabolic speed where others would struggle. In other words, it is not frightening because it behaves monstrously. It is unsettling because it exposes how readily humans mistake appearance for ecological role. There is a long history hidden in that correction. Earlier naturalists often worked outward from form. Teeth suggested diet. Limbs suggested lifestyle. Eyes, fins, shells, and jaws seem to promise a direct route from anatomy to identity. In many environments, that approach works reasonably well. But the vampire squid lives where oxygen is scarce. Food is patchy, and the ordinary visual metaphors of near-surface life become unreliable. It wears the costume of a predator and lives like a collector of drifting leftovers. It resembles a squid and sits closer to the octopus line. Even the label from hell says more about human dramatic instinct than about the animal's actual place in nature. The creature has not changed. What changes, slowly, is the human willingness to admit that classification by surface impression is often a poor guide, where life has followed very different pressures. If the vampire squid unsettles the category of what an animal seems to be, the siphonophore presses on something deeper. A giant siphonophore can grow to lengths around 130 feet, longer than a blue whale. And yet describing it as one animal immediately feels both true and incomplete. Monterey Bay Aquarium notes the extraordinary length. Embry adds the more important complication: siphonophores are the most complex of all colonial animals, operating as integrated units made up of highly specialized zooids. Those zooids perform functions analogous to organs. Some swim, some feed, some digest, some defend, some reproduce. In relatives of siphonophores, similar bodies would separate and become solitary individuals. In siphonophores, they remain joined and function together. This is the sort of fact that sounds clear enough until you sit quietly with it for a moment. Human beings are deeply attached to the idea that a body belongs to one individual, and that its parts, though specialized, are not themselves candidates for individuality. A siphonophore blurs that intuition. Is it a colony? Yes. Is it also a single functioning predator moving through the water as an integrated whole? Also yes. The old contrast between one animal and many animals begins to lose its sharpness. What you are looking at is a living arrangement that occupies the space between those simple options, and does so with remarkable success. The lower ocean contains plenty of strange forms, but few are as philosophically troublesome as a body made from many bodies that no longer live meaningful separate lives. The challenge becomes even harder when you remember that many people first encounter siphonophores visually, through footage in which they resemble luminous ribbons, chandeliers, or drifting chains of glass. Those appearances invite aesthetic metaphors, which are understandable but incomplete. Beauty, here, is only the outer trace of a deeper organizational mystery. Each zooid in the colony is genetically identical and developmentally specialized. A zooid that feeds does not need to reproduce. A reproductive zooid does not need to swim independently. The colony works because roles have been partitioned so thoroughly that the parts are no longer viable as whole animals in the ordinary sense. It is a kind of distributed embodiment, and once you have seen that, the category individual feels less sturdy than it did before. Then there are the deep-sea angler fishes, which approach the same problem from the opposite direction. Here the puzzle is not many bodies forming one coordinated whole from birth. It is two separate bodies meeting in darkness and, in some lineages, refusing to separate again. The Natural History Museum notes that parasitic behavior and extreme sexual dimorphism are seen only in deep-sea anglerfish species. Yale's summary of recent work on serratioid anglerfishes explains why the arrangement may have evolved in the first place. In the vast open waters of the midnight zone, finding a mate can be so difficult that once a tiny male finds a female, losing her may be evolutionarily intolerable. The scale of the habitat presses directly on the architecture of reproduction. The details are extraordinary, but what makes them endure in memory is their calm biological logic. In some species, Yale notes, the male bites the much larger female, remains attached long enough to mate, and then releases. In others, attachment becomes permanent. The male's tissues fuse with the female's body. Their circulatory systems merge, and the male is reduced, functionally, to a sperm-producing organ. Natural History Museum likewise emphasizes that in deep-sea anglerfishes, unlike their shallower relatives, the males can become permanent parasites. That word parasite is useful, but only up to a point. It captures the asymmetry. It does not fully capture the way ordinary boundaries between mate, organ, and individual begin to collapse. The male is not simply visiting another body. In obligate cases, he is absorbed into its long-term operation. There is a temptation, when hearing such facts, to lean too quickly into the grotesque, but that would miss the quieter intellectual force of the example. Human categories around sex, identity, and bodily integrity were shaped by life at the surface, where encounters are more frequent and where most species do not solve reproductive uncertainty by anatomical merger. Serratioid anglerfishes offer a different answer to the same universal problem: how to ensure reproduction in an environment where individuals may drift through darkness for long stretches without meeting a compatible partner. Their bodies preserve the history of that problem. Once again, the lower ocean has not produced nonsense. It has produced a solution that looks absurd only because it was optimized under conditions alien to human experience. The giant isopod introduces yet another variation on this theme, one that at first seems simpler. Nothing fuses. Nothing disguises itself under a false name quite so dramatically. Nothing presents itself as a colony masquerading as an individual. Instead, The animal looks almost embarrassingly familiar, and that may be why people find it so unsettling. Smithsonian Ocean describes giant isopods as crustaceans related to shrimps and crabs, important scavengers of the lower ocean, with huge eyes and a feast or famine lifestyle shaped by scarce food. In photographs, though, they evoke another comparison much more strongly. The ordinary woodlouse, scaled up to an implausible size. The shock lies in the combination of sameness and enlargement. Smithsonian Ocean also identifies giant isopods as a classic example of deep-sea gigantism, the tendency for some animals in deep, cold environments to become much larger than their shallow water relatives. The page notes that this pattern is often linked to low temperatures, scarce food resources, and slower metabolisms. Yet, even with that explanation in hand, the emotional effect remains peculiar. A giant squid looks alien because it is already far from ordinary everyday life. A giant isopod looks alien because it is too close to ordinary life. It resembles something one might find under a damp stone or in a garden wall, then magnifies that resemblance until the familiar turns wrong. Scientific understanding here does not remove the unease. It refines it. The animal remains a crustacean scavenger, part of the cleanup crew, recycling dead organic matter. It also remains an excellent reminder that scale alone can be enough to fracture human comfort with classification. That, perhaps, is why giant isopods have become so culturally sticky. They do not ask us to learn an entirely new shape. They ask us to face a familiar form in an unfamiliar magnitude. The mind oscillates between recognition and refusal. Yes, it is a crustacean. Yes, it has antennae, segmented plates, and a body plan that zoology can describe without strain. And yet it also feels like a thought experiment enacted in flesh. How large can an ordinary design become before it stops feeling ordinary? In the lower ocean, where pressure, temperature, and food availability shift the background terms of survival, familiar blueprints can be preserved and enlarged rather than replaced. That is a different kind of strangeness from the vampire squid or the Seafloor, but no less conceptually important. What links these four cases is not merely that they are memorable or visually unusual. It is that each one makes a different human category less secure. The vampire squid unsettles the relation between appearance and way of life. The Seafloor troubles the distinction between colony and individual. Deep-sea anglerfishes destabilize the boundary between mate and bodily component. Giant isopods disturb the comfort we take in scale as a fixed part of identity. None of these animals abolish scientific description. On the contrary, zoology can say a great deal about them. But the language grows more careful as it proceeds. One must specify lineage, function, developmental history, ecology, and relationship, rather than assuming that the first visible analogy will do the work. That care has a history behind it. Earlier naturalists often named and sorted using the best analogies available to them, which was inevitable. Scientific classification always begins somewhere, and it often begins with resemblance. Over time, however, the lower ocean kept producing forms that made resemblance less trustworthy as a final guide. A vampire squid proves gentler and taxonomically stranger than its name suggests. A predator longer than a blue whale turns out to be a colony of specialized zooids. A fish's reproduction makes sense only after the immensity of its habitat is taken seriously. A scavenging crustacean becomes iconic because it looks like a household creature enlarged by an alien logic of scale. In each case, Science advances by moving beyond the first metaphor without pretending the metaphor had no power. And that may be the deepest reason these animals matter. They do not merely invite admiration for the ingenuity of evolution. They train a kind of intellectual humility. Human beings live near the surface, in light, among abundant visual cues and frequent encounters. The categories that feel natural to us were shaped there. We expect bodies to belong neatly to individuals, diets to align with appearances, mates to remain external, and familiar forms to stay within familiar scales. The lower ocean does not reject those assumptions through abstract argument. It sets living alternatives in front of us, one after another, until the assumptions begin to loosen on their own. So when people speak of the strange creatures of the deep ocean, the strangeness is worth naming carefully. It is not only a matter of fangs, glow, size, or darkness. The deeper strangeness lies in the way these animals press back against the mental furniture we carried down from the surface. They reveal that animal, individual, predator, mate. Even normal scale are not timeless, universal intuitions. They are useful human approximations that work well in many places and then begin quietly to fail. And perhaps that is where the most enduring wonder of the whole journey has been waiting. Not in the idea that the lower ocean contains monsters, but in the gentler, more difficult realization that life has always been wider than the categories with which we first tried to contain it. By the end of this journey, the deep ocean no longer appears as a remote collection of oddities scattered in darkness. It begins to feel like a sustained lesson in humility. Again and again, the creatures of the abyss forced scientists to revise what they thought they knew, not only about the ocean, but about life itself. The problem was never simply that the deep sea was hidden. It was that it revealed, with unusual clarity, how easily human beings mistake limited evidence for complete understanding. The abyss was declared empty before it was truly explored. Its animals were misread because they arrived broken, or glowing, or shaped by pressures and conditions unlike anything near the surface. Even now, many of its inhabitants still seem to stand at the edge of our language, as if classification has reached them, but not fully caught up with them. That is part of what makes this history so moving. Scientific discovery is often imagined as a steady accumulation of answers, yet the deep ocean shows something gentler and more difficult. Knowledge grows by learning how to doubt what once felt obvious. It grows when instruments improve, when methods become more patient, and when observers accept that nature may not resemble the categories they brought with them. In that sense, the strange creatures of the deep are not only biological marvels. They are reminders that the world is under no obligation to fit neatly inside human expectation. And perhaps that is why the deep continues to hold such power over the imagination. It is one of the last places on Earth where discovery still feels inseparable from mystery, where each answer seems to sharpen the outline of further questions. Somewhere below, in cold water and perpetual night, forms of life continue their ancient routines, whether we understand them or not. The search goes on, quietly, dive after dive, image after image, as human curiosity descends once more into the dark, hoping not to conquer it, but to see a little more clearly than before.